Let's start this lecture. Last time we talked about estimation, which is probably the most common type of mathematical statistics problem. And because it's so important and so common, I think it's a good idea to start this lecture with a kind of revision. Let's make a brief summary of what we discussed last time. So it's about estimation. I'm sorry. So it's a kind of summary. To imprint it on your memory. Okay, so we start with this. We have a population variable x. You remember that this kind of variable arises when we choose at random one member from the population, assuming that each member possesses their own individual value of a certain numerical characteristic. Okay, we assume that the law, the distribution of x is known, but what is not known is some parameter. And the most common case is estimating the mean, which is denoted by mu, Greek letter mu. So mu is unknown, and this is what is to be estimated. Now the fundamental approach here is this. We take a random sample, and the result is a sequence of values, sample data. Now if we take a sample of size n, little n, then we get a row of n numbers like this. Okay, now the idea is to use the sample data somehow to estimate mu, which is unknown. Okay, natural enough. Well, and here we distinguish between two approaches. One is to provide just one number as an estimate. It's called point estimate. Point estimate. Okay. Almost universally, for mu, x bar is used as an estimate. X bar, and this is the sample mean. Okay. Well, I say almost universally. We can think of reasons to use some other estimators in particular situations. Okay, now when we introduce this, we mention some properties that we expect of a good estimator. Of a good estimator. Okay. We said that it's a good idea for the estimator to satisfy this maximum likelihood principle, and x bar does satisfy this criterion for such common distributions as binomial, Poisson, and normal. Okay. And also, there are such requirements or criteria as unbiasedness, consistency, and efficiency. And actually, x bar satisfies them all, which makes it a very good estimator for mu. All right, but this is just one number, point estimate. This symbol, hat, is used to indicate estimate, and what's written here means that we use x bar as an estimator for mu, which is unknown. Okay, but we can do better than that. We can make a step forward. Rather than supplying just one number as estimate, we can supply an interval. And this is called interval estimation. Estimation. Okay, like this. Now, what is this about? We start with setting a certain value gamma, confidence level. Well, it has the meaning of probability, and it's going to reflect the degree of confidence that we have in the estimate that we are going to produce. So gamma is a number that is close to 1, typically 0.95 or 0.99. These are the typical values. Okay, and then we take a sample. Okay, we compute the sample mean. Well, here x bar is not the name of the variable. It's supposed to be the little letter x. Here it's the specific value of the sample mean that we compute on a particular sample, and then we construct this interval that is called confidence interval. So D here, I'm not sure it's a common notation for this, but the meaning is the half width of the confidence interval. And then what is the meaning of the confidence interval? The meaning is this, the right interpretation is this. The confidence interval that we construct in this way captures the unknown value of mu with probability gamma. Okay. Well, and this is interval estimation. Okay. Now, to produce a confidence interval, we need sigma, which is the standard deviation of x. And here we have these cases. Case 1, sigma known and n large. Okay, and then x bar minus mu over sigma divided by the square root of n is taken to be the standard normal. Okay, now what is really remarkable about this? This approximation works regardless of the nature of x. The underlying population variable can be of any nature, any law, and still, when n is large, this combination x bar minus mu over sigma divided by root n approaches the standard normal. Okay, but sigma known is rather an exception than a rule. Typically, we don't know sigma. If we don't know sigma, we can sigma unknown. Then we use S, which is called the sample standard deviation, is used as an estimate for sigma. And if n is still large, x bar minus mu over S over root n can still be treated as the standard normal. And we have this third possibility. Sigma unknown, and we use S as an estimate for sigma, and n is not large. But then we assume something else in addition. We assume that the population variable x is normal. Okay. Now, if this is the case, then x bar minus mu over s over root n, okay, follows the so-called student's t-distribution. All right, and this is a complete summary of estimation. Okay, if you know this, nobody can say you don't know mathematical statistics. You do. You know something very important that is applied in practice on the everyday basis, and you can do it when you do your graduation thesis in this school and later on in your career. Okay, I'm glad that I have given you, supplied you with something really useful. Let's move on. Today we are going to discuss another extremely practical and useful section in this science called hypothesis testing. Now, hypothesis testing. Well, by the way, a linguistic comment, this word forms the plural form in a special way. Hypothesis, I here, is singular. If you replace it by an E, Latin E or English E, it's going to be the plural form of the same word. Okay. So hypothesis testing. What do we mean by this? Suppose we have, okay, population variable x, and mu is still unknown, but well, we ask a different kind of question here. It's not. Actually, hypothesis testing is very closely related to estimation. Okay, but here we look at the same problem from a slightly different angle. Now the question is different. Suppose there is a certain specified value mu0. It's a value that for some reasons is of interest to us. Okay? And the question that we ask is this: is mu, which is unknown, equal to this specified value, mu0? Okay? Now the tradition is to state it in the form of so-called null hypothesis. And this is called null hypothesis. Okay, this is the accepted term. Well, and the alternative possibility, mu is not equal to mu0, is called alternative hypothesis. Okay. So, how do we approach this problem? We take a sample. So this is where we start always. Okay, statistics starts with taking a random sample, and as a result, we get the sample data. Okay. All right. Now, the next thing is this. We introduce a test statistic. Test statistic. Now, when we talk about mu, when we perform a test for the population mean mu, then invariably the statistic is this. But hypothesis testing is not limited to tests for mu. We can carry out tests for sigma or for some other parameters. So generally speaking, we have sample data and we introduce a test statistic. And if you remember, a statistic is actually any function of the sample data that is used for the purposes of making inferences, and in this case, making conclusions on the hypothesis. All right, so X bar is the statistic when we do a test for mu. And then we introduce a decision rule. Decision rule. Well, let's write an informal formulation of this, because I really want you to very clearly understand what we are doing here. So when we take a sample, the result is this row of numbers. We introduce it as statistic, and the result is a certain value. Well, if this is X bar, then the value is the value of the sample mean computed on a particular sample. Now, the logic, the reasoning is this. We accept H0 if X bar computed in this way is not very different from mu0. Okay? Let's write it down. Accept H0 if X bar is not very different from mu0. Okay? This is the idea. Now, how do we specify what is very different or not very different? We introduce an acceptance, we construct an acceptance region. Acceptance region. Okay? And the acceptance region is this. It's okay. Now look at this. X bar is supplied with a subscript and an overscript. The subscript CR stands for critical. So we have two critical, we are going to establish two critical values for X bar. L, the overscript, superscript, L refers to lower, and this is U, which says that it's the upper critical value. So we are going to compute two critical values, and the acceptance region is this. If X bar that we get on the sample belongs to this interval, then we say we accept H0. If X bar falls outside it, we say we reject H0. Okay? So these two values the lower and the upper critical value are placed symmetrically on both sides of mu0, like this. So this is the acceptance region, and here we have now we reject the null hypothesis if X bar falls outside this acceptance region. The combination of these two semi-infinite intervals is called rejection region or critical region. Okay. Well, the question now, how exactly we are going to construct this acceptance region. Before we do this, I want you to notice that no matter how hard we try, it's always possible that we make an error. Okay. Now, for any acceptance region, no matter how we define it, it's possible that the actual value of mu is equal to mu0. That is, H0 is true, and still on a particular sample, x bar, that we get on this particular sample may get here or here. Okay? So it's always possible that we mistakenly reject the null hypothesis, which actually is true, on the one hand. And on the other hand, it's possible that the actual value of mu is not mu0, but something else. And still, on this particular sample, the value of x bar that we find falls within this interval. And according to the rule that we establish here, we must accept mu0. So the decision that we make here is not is not absolutely certain. It's not guaranteed against errors. Errors are always possible, and this is inevitable. Now, understanding this, we are going to reason in terms of errors exactly. Okay, we make it our point. We say this. Let's call. We introduce this term, type 1 error, rejecting H0 when it is true. Okay. Again, this kind of error is always possible, and we say that alpha, again, accepted notation, is the probability of type 1 error. And this value has a special name in hypothesis testing. It's called significance level. So not only we understand that this kind of error is inevitable, it's always possible, we actually start with this. We say, we recognize it, and we state a certain value for alpha. Okay, we accept a certain value for alpha, which is called the significance level. Okay. And the typical value is this. Sometimes this is used, and sometimes this is used. Okay. Well, now, suppose we have a large sample, and the value of sigma is known. Okay, and then x minus mu over sigma, and let's write this again. We've already written this formula today, is the standard normal, and and this is what we do in terms of z. In terms of z, we identify such a value of z that the probability contained in this right tail is alpha over 2. And because the standard normal distribution is symmetric about 0, the probability contained in this left tail is also alpha over 2. So the combined probability contained in both these tails is alpha. Okay. Now, actually, this is the acceptance region, formulated, stated in terms of z. So if z corresponding to a particular value of x bar falls within this interval, then we accept h0. If it falls outside, we reject it. Okay. Well, some users prefer to do it just this way, to arrive at the answer using this z. Some users prefer to translate it into x bar. And in terms of x bar, it's going to be this. Okay, again, x bar critical upper corresponds to z sub alpha over 2, and x bar critical lower corresponds to minus that. Okay? So this is the acceptance region, and this is the rejection region, and this is the rejection region. All right. I hope this is not very vague. I hope it's clear. Now let's discuss an example of this, and then it will become 100% clear, I hope. All right. Suppose we observe the operation of a bottle filling machine. Bottle filling. Well, this machine fills wine bottles with wine, okay? And the specification is that this machine must put 750 milliliters of wine in a bottle on the average. But of course, the exact amount of wine put in a bottle varies from bottle to bottle. This is inevitable, okay? There are always some minor factors that influence this exact amount. So from bottle to bottle, this amount varies slightly. But we want to be sure that the mean value is still this. If it's less or if it's greater, we consider it as a problem. It means that the machine is out of adjustment and it needs to be adjusted. Okay? How do we answer this question? Is the mean value of wine put by the machine in a bottle equal to mu0 or not? Now, this is where we apply this hypothesis testing technique. The null hypothesis is that the actual value mu, which is not known to us, is equal to the specified value 750 milliliters, and the alternative hypothesis is that it's not true. Okay, and then we apply this standard technique. But to apply it, we need an assumption on sigma. Let's say that sigma is known to be 2.5 milliliters. How can it be known? Okay, now if it's not a new bottle filling machine, if it has been in operation for some time, then probably we have already conducted tests like this before, okay? And from those previous tests, maybe we have some reasonable estimate of sigma, okay? Or maybe sigma is given in the documentation that accompanies this machine by from the producer. I don't know. Anyway, let's assume that sigma is somehow known. All right, now what we do is this. We need to introduce a value for the significance level, and let me remind you that the significance level has the meaning of the probability of type 1 error that we can live with, okay? It's not a good thing. Any error is a bad thing. But because it's inevitable, this possibility is inevitable, all we can do is to think of an acceptable probability for that, okay? It should be small, it should be acceptable for us. And this is the common value. Most often used value for significance level is this, 0.05. Okay, and now let's do this. We take a sample. We take a sample. Okay, let's say that we inspect 75 bottles filled by this machine. Because N75 is considered a large sample, if you remember, in practice, any sample that is larger than 30 is considered as large enough to apply the normal approximation to X bar. And let me write again this remarkable formula. Now, because N is large, we use this formula, not making any assumptions on the nature of X. Okay, again, this is the central limit theorem. Right, and now what is Z? Okay. Well, now what is this? What is this value? What kind of equation does it satisfy? Okay, this tail must contain the probability of alpha over 2, which is, if alpha is 0.05, it's 0.0225. And the same thing means that the probability associated with the values that lie to the left of this point is 0.975. Let me continue here. And Z alpha over 2 is 1.96. Well, this is a value for Z that appears quite often in hypothesis testing because this value of alpha is very common. Okay? So we have a value for Z, and now X bar critical upper is going to be, well, it's mu 0 plus Z alpha over 2 sigma root n, which is 750 plus 1.96, and here we substitute a value for sigma, which is 2.5 root 75. And the numerical value for this is 750.6. And the lower value, lower critical value, is mu 0 minus this. and it's going to be 749.4. So the acceptance region is 749.4, 750.6. If X bar that we get on a particular sample falls within this interval, we say we accept H0. If X bar falls, well, what does this mean? Look at this. If X bar that we measure on a particular sample is 751, it already means that well, X bar is outside the acceptance region, and we reject H0. Well, it's important to understand what we really mean when we say that we accept H0 or reject H0. If we say that we accept H0, we do not mean to say that we have found out, established that it's true. Absolutely not. Actually, we have no way of establishing that it's true. No matter what we do to the sample data, we will never be able to establish this with certainty. What we say is this: if we say that we accept H0, what we really mean is this: the sample data that we obtained on this particular sample do not give us sufficient statistical evidence to reject H0. Okay? We do not say H0 is true. We say we don't have sufficient statistical evidence to reject it. Okay? On the other hand, if we reject H0, we do not really mean that H0 is not true. Okay? We can't say this with certainty. What we mean is this: the sample data obtained on a particular sample are in contradiction with H0 in the statistical sense. They give us statistical reasons to reject H0. Okay. Now I hope this is clear. All right. Now let's move on. Now this format of the test is called two-tailed. And the alternative here is this: mu0 is the null hypothesis, mu is not equal to mu0 is the alternative hypothesis. But quite often, or maybe more often than this, we are interested in just in the deviation from mu0 in one direction, not in both directions. If this is the case, we apply a one-tailed test. Okay? For example, let's do a right-tailed test. Let's start with an example. Suppose the producer of a certain model of car, certain make of car, claims that the consumption of gasoline of this car per 100 kilometers is just 7 liters, which is very little for this kind of car. Okay, so producer of a car says that mean consumption of gas is 7 liters per 100 kilometers. All right, this is what the producer says, but maybe he is not honest about this. He is not, or maybe not just accurate about this. Suppose we doubt this claim made by the producer, and we perform a test. Now again, you may ask me, what's wrong with just making a test drive just once and measuring the quantity? Now the difficulty is that the actual consumption of gas per 100 kilometers will depend on a lot of things. It will depend on the speed that we keep, okay, on this test drive. It will depend on the traffic conditions. It will depend on the condition of the road. Actually, I'm not an expert at all, but my guess is that the actual consumption will vary from one test drive to another test drive. And if on one test drive the consumption that we observe is 7.5, and we say this and we inform the producer that the actual consumption is larger than he claims, the producer may respond that, okay, on this particular test drive it's 7.5, on another test drive it will be 6.5, and the mean is just as I say, is 7. Okay, so the question is about the mean consumption of gas by this car. Now, how do we state the null hypothesis? The null hypothesis is this, and it's this way. It looks this way in every format of the test. What is different here is the alternative hypothesis. Okay, mu0, 7 liters per 100 kilometers. Now we are talking about the mean consumption of gas, and mu0 is the hypothesized value of mu, and here it's 7 7 liters per 100 kilometers. This is what the producer claims. And this alternative hypothesis reflects our doubts or suspicions. We suspect that the producer is not accurate about this. All right, and how do we formulate the test now? Okay, so suppose we perform 110 test drives. Okay, and X bar is the mean consumption of gas on the sample on these 110 test drives, and then the acceptance region. Now this is different now, different from the previous case. Well, the acceptance region only extends from mu0 to one side. It extends towards the larger values of mu, because this is how we formulate the alternative hypothesis. Okay, alternative hypothesis is mu is greater than mu0. Okay, and okay, accordingly, now X critical bar translates into Z alpha if we interpret this in terms of the standard normal distribution. And now alpha is associated not with two tails, but with one tail, exactly with the right tail, because we are doing the right tail test. Okay, and accordingly, Z alpha cuts off this tail containing alpha now. Okay, and with sigma known, and this is, I'm afraid we didn't mention, suppose we, let's write it here. Suppose we know from some previous data that sigma can be estimated to be 1.2 liters. Okay, and then the equation that we solve to find Z alpha is this 1 minus alpha, and if alpha is 0.05, then this is 0.95. Okay, and then this value x bar critical is equal to mu0 plus Z alpha times sigma root n. And look at this. This is a different value of Z, not Z sub alpha over 2. If alpha is 0.05, then Z sub alpha over 2 is 1.96, as we found in the previous example. But here, Z alpha is 1645. Again, a very common value. So substituting the values, this is 7 plus 1645, 1.2. Here, root, the number of trials is, where is it? Is it 110? 110, and the numerical value is 7.19. Okay. Well, so if you look at this figure, if the sample mean, if the mean consumption computed on this particular, on this series of 110 test drives, if the sample mean is, say, 7.2, then we say that we reject So this is the rejection region. Rejection region. If it's 7.2, we say we have sufficient statistical evidence to reject the null hypothesis. The claim made by the producer is not accurate. But if it's 7.9, then we say, okay, we are ready to accept this hypothesis. We can't reject it. Okay? Well, let's move on. In the same manner, a left-tailed test can be formulated. Left-tailed test. Well, let me just. Well, H0 is always written this way. Oh, just a second. There is something important to be noticed here. All right. Unfortunately, I've already erased it, so I have to write this again. In a right-tailed test, H0 is mu equals mu 0, and H1 is mu is greater than mu 0. Look at this. Something may give rise to questions here. And it's this. These two possibilities are not collectively exhaustive. They do not cover the total range of possibilities. The true alternative to this would be mu less than or equal to mu 0. Okay? So this is not really the true logical alternative to what's written here. A true alternative would be mu less than or equal to mu 0. So why do we write it this way? Now, this is the accepted practice, actually. We simplify the case by writing this null hypothesis instead of this logically true alternative. We simplify the question, simplify the problem. Now, actually, with this statement for H0, it would be difficult to develop the acceptance region and rejection region. It would be a much more complex problem. Okay. So one reason for this is simplification. Another reason is this. Please keep in mind this example about gas consumption. What we are really interested in is whether the gas consumption is greater than 7. We are not really interested in this other possibility. Okay? So what is the point of this testing? The producer says the gas consumption of this make of car is as little as 7 liters per 100 kilometers. And we say, actually, we have doubts. We suspect that actually the mean consumption is larger than that. So for us, the meaningful alternative is this, whether it's 7 or larger. Okay? So we're not interested in this other tail. Well, these are the intuitive reasons for simplifying it this way. But what really happens mathematically when we substitute this null hypothesis, not logically correct, for this logically correct but more difficult thing? Now, when we substitute this for this, we make the acceptance region wider. Okay, so all the possible values of mu in this half-infinite range are kind of condensed here in this formulation of H0. So all the probabilities associated with all the values of mu less than or equal to mu are kind of represented by just this equality. Okay? Now, if you think of it, the mathematical effect of it is that of making the acceptance region wider than it should be. It means that, in simple words, it means that we give H0 some additional credit. Okay? We give it some additional credit. And generally, in the hypothesis testing techniques, this is the accepted approach. H0 is not rejected unless there are definite reasons to do so. Okay? Unless there are statistically convincing reasons to do so. So the H0 is given the benefit of the doubt, as they put it. So here, by replacing this by this, we give H0 some additional credit or benefit of the doubt. Okay? All right, and now in the left tail test, accordingly this, and then and we still find Z alpha in the same way, but actually the rejection region here in this kind of test is not in the right tail. It's associated with the left tail. It's here. So this is the rejection region. Okay? And X bar critical now is mu0 minus Z alpha times sigma over root n. And that's it. So I'm not giving an example for this. We'll discuss a lot of examples when we do practices. All right. Now, the next thing to discuss is the so-called power of the test. All right. First, let's introduce this definition. Type 2 error. So type 1 error, as you remember, is the error of rejecting the null hypothesis when actually it's true. But there is this other possible error. We can mistakenly accept a null hypothesis when actually it's wrong. So accepting H0 when it is wrong. Okay. Now the probability of making this type of error will depend on the actual value of mu. The notation for this probability of type 2 error is denoted by beta, but unlike the probability of type 1 error, the probability of type 2 error will depend on the actual value of mu. But rather than looking at this, statisticians prefer to look at this 1 minus beta of mu, which is called the power of the test. Now, what's the meaning of this in simple words? Suppose mu is different from mu0. Okay? Now, beta of mu is the probability that we accept H0 when it's not true. And 1 minus beta of mu is the probability that we reject H0 when it's not true. So 1 minus beta is a good thing. It's a positive, a valuable property of the test. It concerns the ability of the test to detect the difference between mu, the actual value of mu, and mu0. Okay? It's the probability that the test will tell us to reject the null hypothesis when it's not true. All right. Now, suppose we do a right tail test. We will limit the formulation of this to the right tail test. The other cases are treated in a similar way. Okay, and now mu0, and this is, well, suppose, so this is the rejection region. Suppose the actual value is here. Okay, it's greater than mu zero. Because it's greater than mu zero, h0 is not true. Well, if this is the actual value of mu, x bar has a normal distribution centered here, not here. It's like this. And 1 minus beta, the probability that we reject the null hypothesis, is the probability contained in this tail. Okay? So it's 1 minus beta of mu is equal to the probability that x bar falls to the right of the critical value. Okay? Or in terms of z, it's the probability that z falls to the right of z alpha, because this is associated with z alpha, where z is x bar minus mu sigma root n. Okay? Please notice that here we use mu, the actual value of mu, not mu zero. Okay? Right. So this is what all we can say about power of test. Let me just tell you that whenever a test, an important test is planned, this quantity, power of the test, is necessarily investigated. It's looked at, okay? And the researchers who plan the test ask themselves, suppose the actual value of mu is here. What's the probability the test will detect this deviation from mu zero? And after they have computed this probability, they ask themselves, are we happy with this probability? Are we happy with this kind of sensitivity of the test that we are going to apply? If they find that the probability of detecting a deviation from mu zero is not good enough, is not high enough, then they think of a way to reformulate the test. Okay? And generally, the universal answer, the principal answer to the question of the quality of the test, so the principal way to improve the quality of the test is increasing the sample size. Well, it's a simple answer, it's a universal answer. Increasing the sample size makes alpha less, and at the same time, it makes 1 minus beta greater. So increasing the sample size is a good thing in every way. The only problem is that quite often taking large samples is very expensive or maybe just practically impossible. Okay? All right, so this said, let's just add two things. In all these examples, we assumed that the sample was large and sigma was known somehow. But we also have these two cases. Well, sigma unknown, large sample, then x bar minus mu zero s over root n is treated as the standard normal, and sigma unknown, small sample, and normal x. So this is our additional case. It's x bar minus mu zero s root n is distributed according to the student's t distribution. All right. Now, if you followed my discussion closely, you might have asked yourself this question: is there any relation between this hypothesis testing activity and the activity of constructing confidence intervals? Okay, there are a lot of similarities. There are a lot of things that we do in the same way in both problems. Well, and actually, these two problems, the problem of constructing a confidence interval and the problem of testing a hypothesis, are very closely related. Okay. Okay, let's write it this way. Relation of confidence interval to hypothesis testing. Now, how are the two related? Suppose suppose we have a certain confidence level gamma. The result of this interval estimation activity is a confidence interval that extends from x minus d, x bar minus d, x bar plus d. And again, let me repeat this. It deserves to be repeated. Gamma is the probability that the confidence interval constructed in this way around this random value will capture the true value of the of the mean. All right, and this problem, okay, it relates to this. If we define alpha to be 1 minus gamma, okay, then this problem of constructing a confidence interval has a direct relation to the problem of testing this hypothesis mu equals mu 0. Now, how exactly? Now, we can reason this way. We take a sample. We find the sample mean. Given gamma, which is related to alpha in this way, we construct the confidence interval. And then we accept the null hypothesis here if the confidence interval constructed in this way captures mu 0. And mu 0 is the hypothesized value of mu here. Okay? If the confidence interval doesn't capture mu 0, we say we have statistical evidence to reject the null hypothesis. So mathematically speaking, these two problems are very, very close. The formulas are actually identical. Now, the conceptual difference is this. Confidence interval is something that is constructed after we have obtained sample data, after we have taken a sample and obtained sample data. On the basis of this row of numbers, this is done. Okay? Now, tests are often, or maybe almost always, are planned before any sample is taken. Okay? And this is the right way to do it. Before we even take a sample, we state the acceptance region and the rejection region. And after that, we take a sample and see where x bar falls, whether it falls within the interval or outside it. Okay? What's more, you can imagine the same test applied a number of times to different samples. We first formulate the acceptance region and then apply it to maybe different populations or something. All right. For example, in the test of bottle filling machine, it's possible, and maybe it would be the right thing to do, to construct the acceptance region and then apply this test to different bottle filling machines. If in our plant we have, say, 50 bottle filling machines, the same test is going to be applied to all of them. So there is a slight conceptual difference here, but the mathematics is the same. All right, let's move on. Test for population. So, suppose X, then the population variable is of Bernoulli type. Bernoulli. Which means that X can only take one of two values, 0 or 1. 1 is traditionally called a success. All right, and there is this P probability of success associated with this variable. And P is not known. Okay, now let's consider this example. The producer of a new drug for some serious disease claims that this new drug results in a considerable improvement in the condition of the patient 70% of the time. Well, and this is something very, very good as compared to the existing drugs, okay? This is a new drug that is supposed to be very effective. So drug effective 70% of the time. But this is something that the producer claims. We don't have to trust the producer. Okay, actually, each time the producer of a new drug tries to launch a new product, there is extensive testing performed before the authorities allow a new drug to be placed on the market. All right. Now, one of the questions is this: we want to test. We want to test this hypothesis. This is what the producer says, okay? That the percentage of the patients that have a definite improvement in their condition as a result of taking this drug is 0.7. But we doubt this. We say that maybe it's less than that. Okay, for the population proportion, you can also formulate a two-tail test and a right-tail test, but in this example, it's a left-tail test. All right, now how do we cope with this? Suppose we give this drug to 200 individuals who suffer from this disease. Now, a very interesting and important point here is this. How would you describe the population in this situation? Now, typically, we draw a random sample from some population. What is the population from which we draw this sample here? The difficulty here is this. We are testing a new drug, and logically, we would need to draw a random sample from the population of individuals who suffer from this disease and take this drug. But because it's a new drug, there is no such population. Okay, it's experimental. It's not widely spread. Maybe these 200 individuals are the first 200 takers of this drug. So the right answer to this question is this. Here, we just imagine this population. It's conceived. It's not existing in reality. We just say, okay, let's imagine the population of all the individuals who suffer from this disease and take this drug. We consider these 200 people who actually take the drug within this experiment as representatives of this imaginary population, okay? This is interesting. All right, and suppose definite improvement was observed in 130 patients. Okay, let's denote it by N1. N1 is for success and N0 for failure, suppose. Now, X bar, which is the sample mean, and because we are talking about proportions here, sample mean is also called sample proportion here, is the ratio, the number of successes to the sample size. It's N1 over N, 130 over 200, and the actual number is 0.65. So this is the sample proportion of those patients who get definite improvement as a result of taking the drug. All right, because this is a large sample, we say that X bar minus P over well, let's try to understand what's written here. The sample is large. 30 is supposed to be the boundary, but here we have 200 sample points, which is a lot. Now, and then we say, let's look at this from the standpoint of H0. Let's assume that H0 is true. Then, X bar minus P0, which is the mean. So if H0 is true, then the mean, or in other words, the true value of P is P0. Well, this is P0. Okay? So this is the true value of P, and then the value of sigma. The sigma can be estimated using this complex, sigma X bar. Okay, and this whole thing is normal. All right. Now, in this example here, sigma X bar equals 0.7, 1 minus 0.7, 200. And it's going to be 0.032. So here I substitute the hypothesized value for P, and the sample error. It's called the standard error of, well, generally speaking, the standard error of the mean. But because we are doing a problem on proportions, it's the standard error of the proportion. All right, and because we are doing a one-tail test, the alpha is 1.645, the value that we have already cited today, and P bar critical is equal to P0 minus Z alpha times sigma X bar. And here it's 0.7 minus 1.645, 0.032, and it's equal to, in this example, 647. Okay. So suppose the actual value. Suppose the actual value of and where is it? Okay, this is the sample proportion, the proportion of those who get definite improvement on this particular sample. So what is the conclusion that we make? P0, and this is the critical value equal to. Okay, does this sample proportion fall within the acceptance region? This is the acceptance region. And this value does fall within the acceptance region. So although it's quite close to the boundary of this region, nevertheless we accept H0. Now, there is an important extension possible in this kind of discussion. Look at this. Well, please notice that we use the Z statistic, Z test. And the reasons for doing this is that the sample size is large, it's 200. Okay? Well, this is how it's done most of the time. But you may notice that we don't really have to use this approximation. The normal distribution is really an approximation to X bar, to the sample mean, and it works when the sample mean is large. But because we are so very educated, we can use the binomial distribution directly, because the exact distribution is the binomial one. Okay, I'm not sure. Let me write it here. Let me write it here. So using binomial distribution for the same problem. Okay. Now this is n. This is 0. The hypothesized value is 0.7. So well, 140 is n times p0. So this if the number of definite improvements were 140, that would correspond exactly to the null hypothesis. Now, suppose it's less than that. How do we decide that the null hypothesis needs to be rejected? Suppose the number of patients in which a definite improvement is observed is less than 140. How do we decide that it's so small that we need to reject the null hypothesis? The right thing to do is this. Okay, so we need to identify a certain critical value such that the probability associated with the values that lie to the left of this is alpha. Okay. Now look at this. In this particular problem, the probability that k is less than or equal to 128 is 0.40, and the probability that k is less than to 9 is this. Well, because it's the binomial distribution, and the possible values that the variable takes on are only integer numbers, okay, limited to integers, we can't identify this exactly. So we can identify it, but it's not an integer number. This boundary lies somewhere between these two values. So this is less than 0.05, and this is greater than that. Okay? So what I mean to say by this, if okay, so if we apply this 130, okay, it lies to the right of 129, and the probability that k takes on a value less than or equal to 130 is still larger than that. Okay. Well, using what I mean to say here is this: using this exact distribution here gives us the same kind of answer. Okay. We are only ready to reject the null hypothesis if k is less than or equal to 129. And on this sample, it's 130. So the answer will be accept H0 here too. both distributions give us the same answer? Well, on the one hand, it's to be expected, because we kind of hope that this normal distribution gives a good approximation to the actual distribution. But on the other hand, well, we can think of an example, we can think of a situation where the normal approximation here and the exact binomial distribution give different answer. According to one statistic, the right answer is to reject a null hypothesis. According to another statistic, the right answer is to accept a null hypothesis. Okay, it's possible. So whenever testing like this is performed, the procedure for testing must be very carefully formulated and stated explicitly in the rules or contracts or whatever. All right. If you don't have any questions here, let me mention something else. An alternative approach, p-value. So suppose we do a right-tailed test, and this is mu0, and we take a sample of size n and observe a certain specific value of x bar, the sample mean. We place it on the real line, and then we can ask this question: what's the probability that x bar takes on a value that lies to the right of the value that we actually observe? Okay, given h0. Now, again, we take a sample, we compute a certain value, the sample mean, and now we ask ourselves this question: is this sample mean so different from mu0 that we have reasons to reject h0? And one of the ways to answer this question is this: it's actually not very different, not essentially different from the hypothesis testing procedures that we have just discussed today. It's just another way to look at it. We can do it this way. Rather than constructing acceptance region and rejection region, we can ask ourselves this: suppose h0 is true, what's the probability that x bar takes on a value that lies to the right? This is a right-tail test, to the right of the value that we actually observe. And this is called p-value. So if p-value is less than alpha, we reject h0. And if p-value is greater than alpha, okay, we accept h0. All right, so it's not a different method, it's just a slightly different approach to the same thing. All right, well, I have a few minutes left, and because I'm in such great hurry to give you as much stuff as I can, I think I'll start the next chapter today, and then I'll pick it up next time. And the next chapter is this: chi-squared distribution. Now, the British mathematician of the name of Pearson in the year 1900 introduced this chi-squared distribution, and that was a revolution. This name Pearson is considered as the father of modern mathematical statistics. Okay, so it's absolutely necessary for us to learn this stuff. Now let's first introduce this definition. Suppose x1, x2, xn are independent. Well, this is absolutely important. They're independent and standard normal random variables. So each of these is a standard normal random variable, which is a normal random variable with mean 0 and sigma 1, and they are assumed to be independent. Then then this combination x1 squared plus x2 squared up to xk squared is called the chi-squared random variable with k degrees of freedom. Well, this is something new. This is a new term, degrees of freedom. All right, look at this. We have k independent random variables, each distributed according to the standard normal law. K independent random variables, and for that reason, we talk about k degrees of freedom. Now this notation, chi, this is a Greek letter. Look at this. Maybe it's something new to you. I'm not sure you have seen it before. So this is called chi in English, okay? By the way, in the Russian alphabet, the letter H comes from this letter, okay? So it's not totally strange to this audience. All right, so chi squared with k degrees of freedom. All right, and I have to stop here. I'll pick it up next time. Thank you, see you next time.